Today we are going to do section 1.8, but before we start, I want to scan the books, okay? If you don't need the book scanned, then just fast forward until you don't see the pink thing anymore. Now, so here is, this page we already scanned it earlier, all right? But I want to do it again just for no reason, I guess. So here's the top and here's the bottom. Okay. Next, this is page 38 and 39, the following page. Let's see, pull back a little bit. Is this parallel? All right, that should be good enough. And then a little closer, the top part, and then the bottom part. Okay. Next, page 40 and 41. Okay, here is the entire page. That should be good. Okay, now here is the top part. And the bottom part. Let's see. All right, that should be okay. And finally, page 42 and 43. Let's see, we'll see the whole page. And then a little closer. Okay, and then zoom in on the top. Is it zooming in? There it is. And then zoom in on the bottom. All right, so that should be it. So now let's start section 1.8, but before we get going, I want to quickly show you some of the stuff from Calculus 3 that will be mentioned. Specifically, we're going to talk about the tangent plane, something that you learned in Calculus 3, and I want to show it to you because the tangent plane is slightly long in this description. And so here is the description of any old plane, okay? I just want to refresh your memory. This is on page 195 of the book Calculus 3, which is, I have the free download, the free copy from Openstax. I have the free download under the video description if you want to look at it further. But I don't think you need to. Just looking at this, it should be good enough. Okay, I just wanted you to remind you what was the equation of a plane and stuff like that. And then the next thing I want to mention is, what is that? This is the equation of the tangent plane. That's what it is. Okay, here is how you calculate the tangent plane. If you had a surface and then you had a point, and this is how the tangent plane is calculated. We're not going to be actually calculating tangent plane. I just want to refresh your memory of how it's done. That's it. And then the last concept I want to mention is also from Calculus 3, the gradient. What was the gradient? The gradient was back then defined, and still is now, okay? And the gradient is defined as the fx, okay, I plus fyj. And that's all you need to know for now. Okay, but if you want to review those concepts in more detail, just get the book Calculus 3 and look at it, or look at your own calculus book, either way. Okay, and so with that, let's get on going. So the section starts at page 36. There are some introductory comments, so please read that yourself as well as the rest of the section. Read everything yourself also. But I want to get moving in on page 37 at the top, where we talk about some function called phi. Now the function phi will be defined as f1 times r plus f2 times s. Now this function, then we will then plug something called delta x, delta y in place of r and s. Then we come up with something called a differential. Okay, the differential is then this defined as, let's see, what is that? Defined as a function of delta x, delta y. The reason is because normally the differential holds the point x and y constant. That is, we're calculating the differential at a fixed point x and y. However, of course, we can calculate it at any fixed point, which is why the differential seems to have 4 variables. But most of the time, we're considering at some specific point, and then how that things change as you move slightly away from that point. So that's why we have the delta x and delta y described. Everything delta x is normally considered a small number, but for the differential, you really can define it as any number. Okay, there's no reason to restrict it specifically, but that's what we normally think of it. It's just a small change. We don't have to care if it takes off 1,000,000 miles, then and then the differential is no longer interesting. But in a small range, what happens to this function? Now, so having said that, there's example A where we do the differential just with an example. So please do that one yourself. The example A is, if you just stare at it, you probably can come up with the answer. Okay, so that's how you calculate what du is in terms of delta x, delta y, and then x and y. Just calculate f1 and f2. And then example B is a similar situation. Okay, we're calculating du by the definition of du, which is f1. So you calculate f1, and being this is a composite function, you do the chain rule, and then very soon you will come up with this, right? And if you so much as stare at it, you quickly come up with du will be f1 because the whole thing has to take the partial with respect to x, so you will end up with something like this. All right, so moving forward downward, then you notice that dg, that is each individual function here, we're still talking about example B, okay? So dg would be g1 and according to the formula on top, right? Formula 1 on top of the page. So dg will be g1, g2 times delta x, delta y, and dh similarly. So by the time you look at this equation, and then look at these two, then you realize this is true. Because if you clean this stuff up a little bit, okay, plug this in here, and then you will end up with this equation. So please, again, do this yourself. Although if you stare at it, you'll quickly notice why that is the case, okay? So that's that. Now, so the point of that is that's a, excuse me, that's a quick mnemonic, right? If you have, if you look at it, so then du, which is the same as df, is like it will be just like a mnemonic device where it be f1 dg, the first one, and then f2 dh. So then that's how you can understand this. But is it necessary to memorize it? Not that I remember, but it's there if you need it. So let's move on to page 38. Now we are going to talk about the tangent plane. Okay, here's the equation that I just showed you from Calculus 3. And the equation of the tangent plane, of course, is that thing right there. Okay, and then says so then dz, now we're going to fix some point. Okay, so we have a point that's x at x0, y0, and z0. The book didn't exactly say that that's the point P, but it does. Okay, they're talking P is x0, y0, z0. Now, so then here's the tangent plane, and then we will dz will be defined as we recently done the differential. dz is f1 delta x and f2 delta y. Now to look at this picture, let's I want to mention a few points. And so by its definition, please look at this until it makes sense to you. Okay, on top I wrote down qm from q to m. Okay, that is dz. Now please confirm that yourself right here, because of P is where the starting point, and because dz is calculating from the tangent plane, and that's what that is, okay? And so that's the plane, whereas mn is the actual delta z. That's the actual change, okay, from the function itself. So you can see that there's the tangent plane under normal continuous conditions will approximate the actual function, especially in a small neighborhood, and that's what we are talking about. So the approximation, as you can see, is in this picture at least, is somewhat similar. I mean, somewhat close. Okay, and then so let's continuing. Then the error, of course, is the difference. The difference of if we're approximating the actual function with the tangent plane, then dz is the tangent plane, delta z is the actual length, so the difference is the error. So then the difference is subtracting those two values. Then you get the error right there, which in this picture will be from Q to N. That would be how far the tangent plane is off from the true value. So and next point, then now so far we have assumed that f belong to C1, continuous partial derivatives, but that's actually not necessary because our definition only requires this thing the function f to be differentiable at the point that we care about. So the definition of the differential makes sense. All you need is just that it's differentiable at the individual point, not necessarily belong to C1, and therefore and then if we assume that it is differentiable, we can then use theorem 5, equation 5 on page 17. Now please, I will show it to you right now, okay? And this is on page 17. Look at equation 5. Remember this thing? This is the differentiable definition, which says f of a plus delta x, etc. And the difference of f, the change versus the original, the difference is f1 delta x, f2 delta y, and then phi and psi. Now, right here, now coming back to our current page, we have, let's see, on this side. Okay, now notice that what is dz? dz is exactly f1 delta x and f2 delta y. Okay, so as a result, on the bottom of the page, we can then conclude that let's see. Okay, we can then conclude that that delta z, by its definition, which is right here, is exactly dz plus all the stuff. Okay, when you get all the math come out. So please look at this until you convince yourself that verify that this is the case. Just make sure. Just look at all the variables and realize they're all there. Okay, so let's look at the. Now that we know that delta z is the same as dz plus the error, which makes sense, that's what we said before, because delta z is the concept is delta z is all the way from m to q, right? And then and then qm, this is, let's see, mn then is let's see, mn is delta z, and then qm is dz. All right, so right, okay. Anyway, so that's that. Let's move on to page 39, where we have this particular situation where the limit goes to 0. We have a triangular inequality. Now, please confirm that this inequality does work, so that the limit does go to 0. And and there's a trick to doing this. Okay, so but please try it yourself first, and if you have trouble, I'll show you how. Then look at what I have. Okay, but now try to do this yourself first. Okay, let's see. So we have that this is delta z, which is equal to that. That's fine, and then we're gonna the triangular inequality, which states that let's see, can you see it? Yeah, my pen is running out of ink. So I really should have used a better pen. Anyway, so this thing, okay, I think this is what we started with. You have a whole bunch of, you notice a whole bunch of square root stuff. And eventually, if you do that, then you will eventually get to the inequality. Okay, so I'll let you look at that, and let's just call that done. But anyway, so let's move on then. Okay, that's what I thought. This part, I didn't draw the square root sign all the way across. I don't know why. Okay, so but anyway, you break this thing by substituting this equation in here, and then continuing is yeah, well, anyway, continuing, you will get to that point. All right, and that's that. So in each stage of this, I should mention that the denominator is getting bigger, which means the whole fraction is getting smaller. So that's why it eventually holds. Now let's look at the next example, example C, which we're just going to plug in numbers. So please do that example C yourself. I did it, but then there's not much worth saying here. See, here's example C. I plugged in some numbers, and it works out okay. This is to calculate the approximation of the differential versus direct results to see how far off you are. So so next, let's go to section 8.3, the directional derivative. So the directional derivatives, what is it? It's when you consider the regular partial derivatives, such as partial f partial x, is the derivative in the direction of the positive x-axis. And similarly, partial f partial y is in the y-axis, in the direction of the y-axis. And you might wonder, why do we care about the derivatives happening in those directions? What happens to the other directions? Well, now we're going to deal with the partial derivative in all other directions, and they're called the directional derivative, and they are indicated by something called the psi alpha. Okay, the psi alpha is the direction. Okay, is on the xy plane. It goes at an angle that's alpha, and alpha can go all the way around to 2 pi, from 0 to 2 pi, and it measures counterclockwise from the x-axis just like it normally does. So psi alpha indicates the direction. Now that we know the direction, the directional derivative is defined exactly the same as a regular partial derivative. Okay, it is therefore the limit as we'll slap on the cosine alpha and the sine alpha, because that would that calculates the each side. Okay, so then so as each side increase, yeah. Anyway, so this is del s, this is the sine value, and that's the cosine value. But anyway, that's the definition. We have it equals to del s cosine alpha, and then del s sine alpha added to a and b, and then you do the same subtraction and divide it by the entire length, which would be delta s. Now, as an example, please look at example D and do it yourself. It's just a matter of plugging in the numbers into the definition, and then let the limit go to 0, which I did here. See, it's a quick, short thing, but it's better that you do it yourself. And then, so that we can we can then go to the next page. So now we're on page 40. Let's look at another example. I'll write down page 40. Maybe down here, well, wherever. Okay, now we're in page 40. The next example then, if we have something such as, let's say you calculated something, okay? That is, you calculated that partial f partial psi alpha, as we just now defined, equals to something like that. And then you need to calculate the second derivative. How would you do that? Well, you just treat the first thing, okay, as the function itself in the formula. That is, what's definition again? Okay, so there's partial f, right? So then you treat the f, you plug it in exactly the same way, and that because the partial f, okay, is now the new function, and so you plug it in, and then you come up with something like that. And let me show you the details. So see, what I mean is you give it a different definition to just to keep it clear in your mind. So let's call partial f partial psi alpha g of x, where alpha is some constant. Okay, so and then we need to calculate partial g partial psi alpha, which is what we're looking for. The second derivative is the same as the partial of the first derivative. So you plug this into the original definition, and then which is this thing, right? And then calculate it, and then come up with the delta, come up with what the answer is. In this case, in this example, the answer happens to be 1, but that's how you do it. So please do this yourself to see what is going on. And the whole point of the second partial derivative just means that you use the first partial derivative as a separate function and you just plug it into the definition of the directional derivative and calculate everything out. So please be sure to do that yourself, including the comment below. Okay, verify these comments yourself, where partial f 0 size 0 is f1 and pi over 2 is f2, etc. That is all quite easy to do if you just spend time and look at it. So let's move on to theorem 9, where we have a much simpler way that doesn't have to go along the definition. Okay, what is partial f partial psi alpha in a regular setting? Well, so if f of xy is c1, then we have a simple equation that we don't have to do the limits. Okay, it ends up being f1 cosine alpha plus f2 sine alpha. That is what partial f partial psi is supposed to be. Now, to prove this thing, let's first go to page 13 and look at theorem 3. Where is it? Page 13. Okay, at the bottom of page 13, theorem 3. Okay, we have what is this? Oh, at the mean value theorem. Okay, the good old mean value theorem, where we have the difference of the function equal to that thing where it has theta 1 and theta 2 and all that stuff. Okay, so please look at this very carefully, and because we're going to use that big long equation and plug it in here to make things come out. And so the proof looks like this, and I have it written down here, but please do this yourself. Okay, so here's our theorem. So theorem 9, we're supposed to prove this thing, and I wrote down theorem 3 here. Please do that yourself as well. It's a good idea to write stuff down because it refreshes your brain into taking this stuff more willingly. So we have, remember, theta 1, theta 2 has to be between 0 and 1. That doesn't matter that much, affect us that much, but it's just something to bear in mind. And then we have the definition of the partial derivative. Okay, we're going to start with that, and then we're going to plug everything in here into this thing. Okay, so and to keep things to see what we're doing, we will let delta x in here to be delta s cosine alpha. Similarly, delta y in here will become delta s sine alpha, and then plug everything in here into this thing. Okay, so then we will write this thing out to be that, and then divide by s, delta s, and which will equal to the other side of the equation. We'll plug that in. Okay, I know there's a lot of symbols here, but everything's totally straightforward. You just have to verify all symbols are accounted for, and then allow delta s go to 0. We'll end up with our nice little solution, which is why the book didn't bother to write it all out, because there's a lot of symbols but not much hard work going on. It's a direct plugging in of the mean value theorem, and everything comes out very nicely. That is always nice when the mess clears out and then you see a nice, beautiful, clean picture. Okay, so that's that. Now, so make sure you do all that stuff yourself, okay? And then let's move on to, we're going to relook at example D in the previous page, which said, well, in the previous page, it says example D is, what did it say? Oh yeah, fxy equals to x squared minus 2y. Now, having said that, now we're going to plug in our new theorem, where it says partial f partial psi is simply, where is it? Okay, simply the f1 cosine alpha plus f2 sine alpha. So you plug that in and you quickly calculate something like this, and then we'll try a couple of numbers to see what it looks like. But furthermore, we also have the second derivative, that if you need to know what it is. Let's see, the second derivative, you see I worked it out here, so please do this yourself as well, okay? And then so the partial derivatives, and the second derivative will be you plug that thing into the formula again, and you come up with something, which I came up with that. And then the third, by the time the third derivatives, there is no more variables, so it just becomes 0. Now next, let's move on to the gradient at the bottom of the page. Now we have to calculate, to define the gradient, we're going to define some function f of alpha on a set point AB, okay? So the only thing that's changing in this here is alpha. So f alpha, let's wait for my camera to focus. Why it's not focusing? Come on. There it is. Okay, f alpha is f1 at the fixed point, cosine alpha, and f2 sine alpha. That is that is just a function according to alpha, and we're going to pull out calculus 1 and figure out when is this big F going to be maximum and minimum by taking the derivative. And once we take the derivative and then set things to be 0, we calculate the alphas to have two sets of values like it normally does. And so let's look at the two sets of values, and you notice that if you put in the positive values in, that is the sign, they're not actually positive. I just mean that in here there's no negative sign, okay? There's one set that has that doesn't have negative sign, and the other set does have negative signs. Now the one that doesn't have negative sign, if you were to plug it into the original function, you will quickly notice that the function will be bigger than 0 all the time. It equal to the square root. I mean, squared divided by square root. So then it equals to the square root of f1 plus f2. Just plug in the sine alpha 1 and cosine alpha 1 into the original big F. Okay, and then you will see this is the case, and it's always bigger than 0, so that has to be the maximum. And the other one is always negative, so it has to be the minimum. And well, please do this yourself, of course. Now that we have calculated that, then we can do something called the gradient. Oh, I should also mention that if f1 and f2 are both 0, then you can't do the division anymore, but by then everything is 0, so the directional derivative is all 0, everything's just 0 and nothing's happening. Okay, so let's move on to the definition 9, where the gradient, this is the same gradient as I showed you in the beginning of this video, where the gradient is f1i plus f2j. However, this gradient, the author for some reason doesn't want to mention vectors. Okay, so he's defining it in a rather roundabout way, which is okay. It's still consistent with our section. And notice this. It says the gradient is a vector of the magnitude f1 squared plus f2 squared square root, okay, the Pythagoras theorem. And then in the direction of psi alpha 1. What was alpha 1 again? Alpha 1 is the maximum, right? And the other, whereas alpha 2 is the minimum. Alpha 2 is the angle that is that goes to the other way. That's the minimum one. And well, remember, alpha 1 and alpha 2 different, only different by pi, because the way that the sine and cosine solves themselves. Okay. So anyway, so the psi alpha 1 is the direction where the gradient will be defined in this book, which is how the gradient, how it is too, okay? If you use the I and j notation, the vector notation, for whatever reason your book doesn't want to bother bringing in the I and j, which is okay. This still makes sense. So we'll just go along with it. And so with that, let's please do example E, which is a quick sample of how things might work if you plug in certain numbers to calculate gradient of this sample function. And I believe I did that. Let me show you. So example E, yeah, I have it right here, right? You just plug in the numbers, calculate F1 and F2. I did it the old way where we have I and J. I feel like that seems to be simpler, but it doesn't matter how you do it. You just the point is the magnitude will be square root of 26, and then sine alpha 1 and cosine alpha 1 equals to those values. And so please do that yourself. So by now we have proven theorem 10, which says if you have a function where the two first partial derivatives are not zero at the same time, then the maximum directional derivative is the same, is going to be equal to the square root of f1 squared plus f2 squared, and which is the value at f of the directional derivative at alpha 1, where the directional derivative is in the direction of grad f. Okay, everything evaluated at a, b, and defined by equation 3 on top. Like I said, that sounds like a slightly convoluted way of defining grad, but that's what the book wants to do, so we are going to do that. And so we have come to the end of this section. For homework, please do I think this is it. Yeah, 1.8. So for homework, please do problems 1, 2, 4, 7, 11, 12, 16, and 17. I also typed the homework into the video description. If there's ever a discrepancy between the two, that's just because I typed it wrong. Because we always start in my notebook. So please go do your homework, and when you come back, I want to talk about them. And now that you're done with your homework, let's look at problem 1. We have some function. We're just trying to calculate the maximum and minimum of these things. So yeah, I guess that's all I did. Okay, that is so you calculate sine. By the time you calculate something, you figure out this sine alpha 1 will be 4 over 5, and cosine alpha 1 is negative 3 over 5. So then the function f will be equal to 5 at the maximum or minus 5 at the minimum. Yeah, I think I just went directly from equation 3 on the previous page. So that's that. Now next, let's look at the next question, which I thought it was very funny. And let me show you what I mean. Now let's say we have f of xy, and we're calculating the value of the f of xy at some specific point, 0.9, negative 1.2, in radians by use of tables. Now what does the book mean by that? That really cracks me up, because the tables are used back in the day when there was no scientific calculator. Okay, and the reason I know that is because I used tables myself back in the day. Now you might ask, are you that old? You know, this book is remember, this book is copyright 1948. No, even I'm not quite that old. I mean, you'd be over 100 years old or something. But the reason I had to do it is because my school at the time was into and they despised the newfangled calculator and think the old tables are better. And if you don't know how, you think, how would you use tables? Yeah, if you don't know, you don't ever want to find out. Okay, I'll never do that again. But it does crack me up to see that right now. And because I was forced to do that when I was a kid. Boy, did I hated the tables. Anyway, our life is much more improved now. Okay, we no longer have to deal with the horrible tables. That was disgusting. Anyway, so then to do this thing, please refer to example C, okay? And you do exactly the same thing. You plug in some numbers, I think, and then calculating various things, and then calculate what the difference is between the estimate and the real story. But for the days of the book, the estimate is easier to do, because then they don't have to look at the horrible tables, okay? And which is why they did it. And anyway, so that's that. And next, let's look at problem number 4. Problem number 4, please refer to example B on page 37. And we're just going to do some quick partial derivatives, okay? And everything does come out very nicely, as you can see, once you have everything written out and everything accounted for. Now, I just noticed that for the homework assignment, I forgot to write down problem 5, okay? So I'm gonna type it into your homework assignment. So don't forget to do for problem 5. Well, anyway, so let's talk about problem 5 right now. If you haven't done it, please do it right now, okay? I think it's just a short little thing, so it won't take you long to do it. Now, for problem 5, we are just calculating some partial derivatives. See, not very long, and so go ahead and calculate that, and everything comes out well nicely. Okay, so that's problem 5. Now, problem 7, I think, is a similar story. It's just a matter of let's calculate something, and you plug things in just like the definition says. Specifically, pay attention to theorem 9 on page 40 and follow that, and everything should come out nicely. I think I messed up a bit here, but eventually I pulled myself out, and that is the right answer. Okay, so next, let's look at problem 11. Now, problem 11 is, well, that looks like we're just going to go by the definition. So the definition of the directional derivative is on page 40, theorem 9. We're going to go by theorem 9. Okay, so if you write it in, then you notice you have a sum of angles of sine and cosine. So what are we going to do? We're going to pull these identities out back from trigonometry and then plug things in. And once you plug it in, you notice that two of these things, this message, like that one and that one, cancel identical, so that they're able to cancel themselves out. And as a result, will end up with just this. Okay, and then it does equal to, when and all is said and done, it does equal to the cosine phi grad f that the book wants, and that is the answer. Now, in problem 12, we're suddenly stuck in doing some geometry, which is okay, all right? And so we have that circle, and we have perpendicular, and we have all that stuff, and we need to calculate the equation of lines. So that's what I did, okay? And we have something about, well, I need to figure out the slope. Remember the slope, which means something about the perpendicular line has to be the reciprocal of the slope, and not just that. We have to also have, did I mention that? Yes, it needs to be 1 over. Okay, the perpendicular line is the negative reciprocal. All right, so having said that, then eventually I was able to come up with the equation of the line. And continuing on the next page, we have we will calculate this thing. And in calculating this thing, we have so after plugging into the formula of the directional derivative, I calculated that the cosine alpha is negative 3/5 and sine alpha is negative 4/5. And then plugging things into the equation, I was able to calculate what the partial is at that specific point, which does turn out to be correct, okay? Which is fine, but we're not done yet because we have to prove something. Now, notice specifically this value right here. What does that mean? That is the angle alpha. Okay, not counting the actual angle, of course, is bigger than that, but this is just there's a name for this thing, I don't know, the generic angle, complement something. Anyway, this is the angle that is, if you're not worried about where it is. So alpha is here. Alpha is the angle that forms the 3, 4, 5 triangle. Now, knowing that, we are going to do the proof of the second part by drawing this triangle right here. Here's alpha, and then here's gamma. Gamma is what we're looking for. Okay, here's beta, which there is, and this angle right here is, there's a relationship of 4 and 7. And remember, alpha we know how big alpha is because alpha is defined by this relationship right here. Now, knowing that, we are going to do, what is that? That is, the difference of cosines, okay? Cosine difference of angles. Pull that formula out somewhere, right? And then plug everything in, and it will end up being what we want. So that cosine of gamma does equal to this. And you calculate it based on this information, okay? Where beta is a relationship of 4 to 7. And the alpha information, which is alpha is 3/5 for cosine alpha. And also this triangle right here. So we are doing a bit of basic geometry here, which is that. Okay, that's good enough. Let's move on. Next, let's do problem 16 and 17. So we have right here the the number 16, we have this function and we need to find the pattern of the nth derivative. Now notice that we're looking for nth derivative and f is only up to the power n. So the two numbers are the same. What happens, and that matters, because as we calculate it, things a pattern will begin to emerge. So first we calculate the first derivative, which is right there. Okay, we're doing this based on theorem 9 on page 40. And then we do the second derivative, which means we plug everything into the theorem 9 again. Okay, and then we end up with something like that. But eventually we notice that big mess, which you will get. Okay, make sure you do get a big mess. If you don't get a big mess, that means you missed something. Okay, everything needs to be plugged in there, and the whole thing expands into a giant pile of stuff. But you think, wow, that's only the second derivative. How far are we gonna go? Then, but luckily, this giant mess condenses into a more manageable formula, which is right here. See, and so by now we see a pattern, and we're just going to say, yeah, that's the pattern. So that is the second derivative will be this pattern, and then the third derivative is something like this. We can calculate the third derivative based on the second derivative pattern, because the situation is the same. And so eventually the nth derivative then will be the n factorial, and then the x plus y will disappear because it will end up with this power n minus n. And it is so the rest of it will come out nicely, and that is the answer, which checks out with the back of the book. So yeah, that's always nice when the answer is finally right. So that's problem 16. Next, let's look at problem 17. You might think the problem 17 looks confusing. Well, that just means we are going to. Well, we're going to do it anyway, okay? The fact that it's confusing means nothing. We're going to do it just like it says. So what that means is we have a function f, for which we can calculate f1 and f2 over there. Now the grad f, by definition, is this thing, okay? And we can plug the variables in and come up with something like that. So the grad f is another function. Okay, let's call it gxy for clarity's sake, which is x squared plus y squared. So gxy is as good a function as fxy, right? Which means we can calculate g1 and g2, and more importantly, we can calculate grad g. Okay, the absolute value of grad g is it just means the grad of f. Okay, that weird notation, that's all that means. So we're going to do grad g the same way we did grad f, which is the square root of g1 squared and g2 squared. And once you realize that, then the equation we're trying to prove comes out nice and easy. And that, I believe, marks the end of this section.